Hello, and welcome to today's webinar, Belimo and Emerging Data Center Technologies, Single and Two-Phase Cold Plate Solutions. We appreciate your joining us. Our presenter today is David Candell, Data Center Solutions Architect for Belimo. My name is Maureen Williams, and I will be your moderator. As a friendly reminder, these webinars are recorded and will be posted to Belimo's YouTube page and Belimo University, our free online training platform located at belimouniversity.myabsorb.com. If you're experiencing any technical issues, please open the chat box in the bottom right corner and let me know so I can assist you. Please write your questions in the Q&A box, and David will be happy to respond to you by email. Without further ado, I would love to introduce you to our presenter, David Candell.
Hey, thanks, Maureen. Appreciate it. And thank you so much for everybody who's joining us for our webinar today. My name is David Candell. I have worked for Belimo for what seems like forever, so hopefully I know what I'm talking about. Just a couple of housekeeping things. We're going to talk about liquid cold plate solutions today, single and two-phase. This is based on a blog series that we are doing. If you're interested in reading the blog article that corresponds with this, that's what that QR code is right there on your screen. It will also be on the closing screen, so if you miss it this time around and then you want to catch it later, it'll be there. Also in the bottom right corner, that's the email address for the training group inside of Belimo. So if tomorrow you're walking around and you're like, oh, I wanted to ask a question during that presentation, please send it to that email address. They'll get it over to me and I'll get back to you. So let's talk about it. This one's a little bit different. There's not a lot of Belimo product involved in our webinar today. What we're really talking about is technologies that we're finding in this liquid cooling avalanche that's coming into the data center world. So most people have heard of cold plate. They're usually talking about single phase cold plate. We're going to also talk about two-phase cold plate. We're going to just kind of climb into the rabbit hole a little bit and give everybody a little bit more information about how this technology works. Now it's a Belimo presentation, so I'm going to talk a little bit about how our products integrate, but that's really not the function of what's going on here. Let's talk about how we got here. So when we talk about cold plate, what we're really talking about is the change in heat densities inside of our data center. So I think we all know that there's been this big shift, or at least we've heard about it, but where did it come from? How did we get here? What's going on? It's always interesting to look back a little bit. Take a look at what happened before and why there's such a stark change right now in 2024. Why is everybody freaking out all of a sudden and making all of these changes? Let's start with this graph here. This is courtesy of the Uptime Institute, and they do these wonderful surveys and informational gathering, and they took a look at average kilowatts per rack. Now, if you're not from the data center universe, this is a pretty common measuring stick of how much heat we're creating or how much energy we're using. And so in 2011, for example, according to this chart, a rack of servers, so that's the box that the servers sit in, put all those servers in there, and the rough amount of heat that was coming off of there was 2.4 kilowatts per rack. And again, this is based on the Uptime Institute's research. 6 years after that, we went to 5.6 kilowatts per rack, according to the Uptime Institute data. Now, that's a pretty substantial increase. That's more than twice as much heat over just a 6 years worth of time. It's noteworthy to notice that there's always been fairly substantial growth in the heat density of these servers. When we went from 17 to 2020, we took another sizable jump. And so you can see that we've gone up. But as recently as 2020, and in fairness to this data set, they eliminated some of the really high heat density applications. They were looking for the average of the quote normal installations. We're somewhere in the 8.5, maybe 10 kilowatt range. For a long time, in the last years leading up to the most recent few years, that 10 kilowatts per rack was sort of, like, yeah, if we're in 10 kilowatts per rack, that's kind of a good way to go. We've just destroyed these numbers in the last couple of years. And what is that all about? That brings us to why we're here, which is the AI market. The artificial intelligence marketplace is what's driving all the changes in these data centers. So in order to understand why that's being driven, we kind of need to get a reflection of what's going on with businesses, with individuals, with the consumers of AI in the marketplace. So what does that look like? So I found this interesting study that Forbes put together, and this study's a couple of years old for fairness. But in the study that they did, they saw roughly 65% of business owners that they interviewed believe that AI will increase their productivity. Similarly, roughly the same amount of business owners thought that AI would improve their customer relationships. Well, this is a good thing, right? But if you look at this data for what it actually says, is that 2/3 of business owners aren't currently using AI very much, but they think it's their future. So this is where we are now. It's becoming the present for all these business owners. Suddenly the AI tools are available or becoming available, and the consumption is ravenous by the marketplace. What about individual people? Because I think businesses operate a certain way and they tend to be maybe a little bit more conservative about adapting technology. What about individual people? Well, the Pew Research Center did a study, and I like this one a lot. They said a little over a quarter of Americans say that they interact with AI several times a day. So where am I interacting with AI as an individual? Well, anytime you shout at your phone a command, hey, phone, look this up, do this, set a timer, remind me about this. Well, we're using an AI engine to do that. Obviously, the obvious ones like ChatGPT and all of those types of things, all AI based. So they're saying like 27% of Americans several times a day, an additional 28% of Americans, at least a couple days a week. So we're like over 50% of Americans are using AI regularly as part of their life. The following stat might be my favorite statistic of all time. So ChatGPT was released. And when ChatGPT was released, it was like a beta release. It wasn't a productized thing. They were just like, hey, let's throw this out into space and see if it works. They knew it worked, but they wanted to see if it would gain any traction. So ChatGPT was released with no fanfare, no marketing, no blitz of social media, and they had 1 million registered users in 5 days. In 5 days, this thing that they just went, here you go, play with it, 1 million people signed their name and said, I want to play. And within 60 days, they had 100 million registered users. This blows away everything, by the way. This is faster than TikTok, Spotify, X, any social media platform. No one ever grew like this. Individual people are consuming AI at a voracious rate. Here's another interesting stat. An AI search uses approximately 10 times more energy than a typical Google search, meaning if I type, how do I make chocolate chip cookies into Google, I'm going to get an answer. I can say, hey, Google, what's a chocolate chip cookie recipe? I'll probably get the same answer, but I've used 10 times as much computing power to do it. Oh, and by the way, if you want to, quote, be conservative or conservation of computing power, and you don't want to do that. Well, AI has, Google AI is now generative in your normal search, and so is the thing from Microsoft, and so is the thing from this one and that one, and that we can't get away from this. It's just true. Every kilowatt of electricity that's used in a data center, almost 100% of it becomes heat energy at some point. And in our industry, that's what we have to pull back out of there. So when somebody talks about building a 10 megawatt facility, that facility is going to produce 10 megawatts of heat or damn close to it. So how do we do this? How do we do thermal management? Thanks to Vertiv for creating this chart. This was in a paper that they wrote. I think it's really illustrative. When we start to look at the types of technology that can go ahead and do this cooling, we see things like perimeter crack and crawl units, raised floor and containment. We're at the 15 kilowatts per rack and under. Then we get to row-based cooling with containment. So that's your hot aisle, cold aisle. And then you can do some good work there, but we're still in that 25 to 30 kilowatts range. That's basically the physical limits of air cooling. Then you're going to get into hybrid things like rear door heat exchangers, and then we're into true liquid cooling when we're at that 50 kilowatts and up range. 50 kilowatts per rack. We were just talking about 4.6 and 8.5. How did we get to 50 kilowatts per rack? Well, let's thank these guys. NVIDIA is not the only company making crazy computing power, but they certainly are at the forefront of this. And this is their new super server GPU, CPU rack system. I don't even know what you call this thing. I do know that this is 120 kilowatts per rack. 120. Let's talk about 120 kilowatts per rack. Do you know how much heat this is? All right, let's take this as an example. This Weber 3-burner grill is rated at 30,000 BTUH. So we can cook a steak on there. We can cook our afternoon or weekend meals on there. What is 30,000 BTUH? Well, a little math will tell us that that's 8.8 kilowatts. And that means that there's roughly the heat equivalent of 13 and a half of these grills coming out of that server rack. So thanks to my friend Don Mitchell over at sorry, he's my friend through OCP. He works for Victaulic. He gave a wonderful presentation last week at the DCD Connect conference in Virginia, and he used this image to show us how much heat one of those servers put off. Ironically, he had this server, this image was made by ChatGPT, so we caused the problem to show the problem. If you're not familiar with OCP, it's the Open Compute Project. It's a wonderful third-party organization full of a lot of great minds from our industry, the data center industry. Belimo is an active part of OCP. You can go right there and read detailed white paper information about cold plates, how they're built, how to use them, all kinds of stuff, way deeper than we're going to get into. But I always like to give a nod to these guys because they're making wonderful reference designs, all kinds of great documentation, and it's a nonprofit group. It's for the industry. They do some wonderful work over there. So if you really want to learn a lot more about this, feel free to go down and check out the Open Compute Project. And certainly their work they're doing on liquid cold plate. All right, let's talk about direct-to-chip cooling. So direct-to-chip cooling, also known as cold plate, they look like this kind of thing. It's just a little small heat exchanger, and you mount it directly on the server. You put it right on top of the chip that's making all that heat. And the inside of that thing might look something like you see here. The fluid's going to run through there in a reversing pattern like that. Sometimes they kind of have a wavy profile. Sometimes it's just a bunch of fins in there that they push across. Each manufacturer has slightly different designs and variations about how they're going to pull heat out. You get some of these thermodynamics guys, they'll figure out the best way to pull heat out through heat exchangers. But in general, that's how they're put together. When we install them on the server board, they look a little bit like this here. So you can see these black rectangular pieces in here. That's your cold plate. So there's 2 of them marked on this half server tray here, and we're bringing the fluid in. These are kind of piped in series, and it comes back out the other side. So an actual full board server might have 3, 4, 5 of these cold plates in there. Sometimes you'll have, as you see at the bottom here, multiple supplies and returns so that we get the cooling capacity that we need. Interestingly, cold plates only remove somewhere between 60 and 80% of the heat that's being created. And so even when we're pulling the majority of the heat out, we're never going to be rid of the air cooling portions of a data center. There's enough residual heat, even when we pull lots of it out, that we're going to need a nice, robust air cooling system in addition to these liquid cool type solutions. Direct to chip cooling or cold plates can cool racks up to 100 kilowatts per rack and even more. If we're being honest, you can just put more cold plates in there to pull more heat out. We can change the physics of what's going on with them. Lots of things we can do to increase that capacity. That NVIDIA unit that we looked at before is being cooled by liquid cold plate. And so we know that it can do that 120 for sure. What does this look like from a design standpoint? Well, this is like a rack with 4 servers in it. In general, the fluid's coming from a CDU of some kind, and it's usually coming through like a braided hose or a flexible tube of some kind, and then we'll go to a manifold, and that manifold will have additional tubes that go to each server, and then it's returned out the other side. So it looks a little bit like a building in that we're serving multiple floors of a building, but really we're talking about relatively low pressure losses in all this piping, and so we can ignore some of the things that happen in building type designs in terms of pressure disproportionate distributions and things like that. And then in general, we're going to have a control valve on the return side. That control valve typically isn't modulating. What we're doing with that control valve is making sure that we have the absolute right flow for those 4 servers. Why would we not modulate that? Obviously, these computers are going to ramp up and ramp down and create different amounts of heat depending on what's going on. The answer lies in how quickly we get changes in computing power. We couldn't adjust the flow nearly fast enough to keep up with the instantaneous demand of changes in those servers. Now, do I think in the future we could use AI and other smart things to predict the changes that were coming and proactively make changes in flows and things like that? I think that's a very real possibility. But today, we're usually going for a single flow. What's pictured there is the Belimo EPIV, and we love this product in this solution because you can program it for a specific flow rate. You can network that guy, and so if I need 22 gallons a minute for those 4 servers today, that valve's going to give you 22 gallons a minute all day, every day going through there. And if you need to change the flow rate to that because you put in different servers and suddenly needed 28 gallons a minute, as long as there's capacity left in that valve, you simply reprogram it or give it a different control command, and now it's going to control to 28 gallons a minute. The Belimo EPIV is really good at being flexible, and it makes you a little bit future-proof if you size it properly on the way in. Little bit of teaser, we're going to have a blog post coming up, followed by a webinar on a really specific feature inside the Belimo energy valve, where we're able to use differential pressure control across a rack, and it allows us an amazing amount of versatility in our operational sense. But I don't want to steal all the thunder on that, just a little teaser for our next blog post. Let's talk for the last few minutes here about 2-phase cold plate. So you're probably familiar with the idea of 2-phase heating or cooling. This is the idea that we're going to change phase as a way to move heat from one to the other. We're using the latent heat of phase change instead of the using the change in temperature to get there. These are usually pumped refrigerant systems, so this is not like an air conditioning unit where we're using a compressor. We're usually just using a pumped two-phase system, and we're using a specialized refrigerant that will go into these cold plates and actually vaporize inside of the cold plate, pulling the heat out of there. From a system geometry standpoint, what we're going to do is a little bit different. You're going to have some kind of refrigerant reservoir and a refrigerant pump, and it's going to pump that fluid up through some kind of refrigerant valve. And then into these, obviously we're using different types of cold plates. They have these mini channel evaporators. There's also these types that just have the like fins inside of it, and a reservoir of that material kind of fluid comes in, and it just starts to vaporize in that space. Once we have kind of a mix of liquid and vapor, it's going to exit out the other side. It goes through some kind of condensing unit. The heat is pulled away back to reject it, and the now condensed refrigerant goes back into the reservoir. So it's a very basic refrigerant loop. It's not nearly as complicated as a compressor refrigerant type loop, but we are changing phase and we're getting great thermal advantage through that phase change. So we're enhancing our heat transfer efficiency. We're increasing our cooling capacity. The reality is we can just pull more heat out this way than we could with just a single phase type of heat exchange. And the other nice part is that we get a much more uniform temperature distribution when we do two-phase. So what I mean by that is when I'm changing phase, I'm not really changing temperature. So the fluid is the same temperature as it goes across that cold plate. It pulls heat out much more uniformly. And so that's kind of an interesting advantage to evaporative cooling processes like two-phase liquid cold plate. At this point, Belimo's tinkering with some refrigerant control type valves. We don't have a massively marketed product for that yet, but don't hold your breath too long. We will be in the marketplace with that. We think this is a nice emerging technology. So before we close out today, always remember great data center solutions from Belimo. On the left side, you have our friend, the EPIV, which we talked about, and then his big brother, the Belimo Energy Valve, which does have that ultrasonic flow meter and the full BTU meter integration in it. Lots of great solutions from Belimo. Please reach out to us, reach out to your local sales vendor. We're always happy to chat about the clever solutions that we have. Thanks so much for joining us. We love these little short form webinars. I hope you got something out of it. Remember the QR code on the bottom left there, that'll take you to our blog post. The email address in the bottom on the right is if you have a question later on and you want to shoot it out to us, please do. Anybody who put questions into the Q&A, we will get back to you within a week or so via email. So I'm going to bring Mo back in to close this off. Maureen, if you could join us again.
Absolutely. Thank you all so much for attending today's webinar. I'd also like to thank our presenter again. David, thank you so much. If you would like to watch this webinar again or recommend it to any friends and colleagues, it will be posted to our YouTube page as well as Belimo University. If you had asked questions, we will be sure to answer them all by email. And as David mentioned, if you should think of any further questions, you can always reach us at training@us.belimo.com. Thank you and have a great day.